So today we are going to start February-March 2022 paper 4-2. Let's start with question number 1. Iodine is found naturally in compound in many different oxidation states. So, okay, iodide ions react with acidified H2O2 aqueous to form iodine and water. The reaction mixture is shaken with a cyclohexane to extract iodine. Cyclohexane is immiscible with water. If we look at the first statement, they are telling us that when iodide reacts with acidified hydrogen peroxide, we are going to get iodine and water. Okay. What they are asking in part 1, identify the role of H2O2. Okay. In its reaction with iodide ions in acidic condition, and whenever examiner says acidic condition, it means we use hydrogen ions in the equation. So iodide ion, hydrogen ions, and hydrogen peroxide ion forming iodine and water. Now, this equation is unbalanced. It is not balanced. So we have to first balance it. So if I go for balancing, see the net charge over here is 0. Hydrogen is +1. And there are 2 hydrogens, which makes the +2. And then the oxygen have -2. On this iodine molecule, the oxidation number is 0. And here in H2O2, the oxidation, the net charge is 0. The charge of hydrogen is +1 times 2. So it means oxygen must have a -2 oxidation number, but there are 2 oxygens, which means each oxygen have a -1 oxidation number. Okay. Here, if you see, iodine have a -1 charge. So if you see, you can easily see that iodine is changing from -1 to 0. And here we have a 2 iodine molecule atoms. So I would put 2 over here. So if you see, we can say that there is a loss of 2 electrons. Here I have only 1 oxygen, sorry, 2 oxygen, and here I have a 1 oxygen. So I would put 2 over here. Then from this -1 to -2, there is a gain of 2 electrons as well. Now, you just need to balance the equation. Iodine is balanced, oxygen is balanced, hydrogen is left. We have a 4 hydrogen over here on the product side. And on the reactant side, we have only 3 hydrogens. So I put 2 over here before H positive to balance the equation. Is this understandable to everyone? Okay, I do one thing. So this is the equation. Now, if you see here, oxygen is -1 and becoming -2, which means oxygen is undergoing reduction. And oxygen is undergoing reduction, then it means H2O2 is oxidizing agent. So the role they have asked for, the role of H2O2, it is oxidizing agent, and we have completed the equation as well. Yes, is this understandable to everyone? Yes, is this clear?
Yes, sir.
Okay. Now, question number 2. It's of partition coefficient. 15 centimeter cube of C6H12 is shaken with 20 centimeter cube of an aqueous solution containing iodine until no further change is seen. Okay. So according to this information, that iodine is initially present in water in an aqueous layer, and we have shaken the iodine, this solution of iodine, with hexane. And if you see over here, they have given you this statement that the reaction mixture is shaken with cyclohexane to extract iodine, which means that iodine is also soluble in C6H12, right? So if it is soluble in C6H12, so it means that some of the iodine may get dissolved in hexane and is actually extracted from its aqueous layer and gets dissolved in a hexane. Is this understandable? Now, it is found that 0.390 gram of iodine is extracted into C6H12. Okay, so it means that at when the equilibrium is established, that 3.90 gram of iodine is present in hexane. The partition coefficient of iodine, okay, between hexane and water is 93.8. Okay, it's cyclohexane. Calculate the mass of iodine that remains in the aqueous layer. Okay. So first I would write this equation that aqueous iodine from the aqueous layer is getting dissolved in a cyclohexane layer. And they have given us the information at equilibrium, that equilibrium there is 0.390 gram of iodine is present in the cyclohexane, and they are asking for the amount of iodine present in aqueous layer, and we consider it as X because we don't know. They have further provided you the KPC partition coefficient, that is 93.8. So if you write the KPC expression, KPC is equals to concentration of iodine in cyclohexane divided by concentration of aqueous iodine. Let me recall you one thing. Most of the time, we use the unit for concentration is mole per dm cube, but concentration can also be expressed or written in gram per decimeter cube as well. So there is no need to convert it into a moles. We have provided with the grams, and we know how much cyclohexane is used, 15 centimeter cube. So in numerator, I would keep the values that 0.390 divided by 15 over x. X is the amount of iodine at equilibrium in aqueous layer, and the volume of the aqueous layer is 20 centimeter cube, so x over 20. And now you have to find, okay, so it means, 1 minute please. Okay, so the value of KPC is 93.8 multiplied by x over 20 is equals to 0.390 over 15, and then further x is equal 0.390 over 15 multiplied by 20 over 93.8. Can anybody tell me the answer?
5.54 into 10 to the minus 3.
5.54 into 10 raised to the power minus 3.
Grams.
Okay. And as it's the unit is gram. Okay, that's fine. Now, next part, suggest how the value of KPC of iodine between hexane 2-on and water compares to the value given in A2. Okay. Yes, can anybody comment on this?
It's lower
Why it's lower?
because I2 is more soluble in hexane 2-on.
Okay. They are actually asking if somebody is confused and don't know what they are asking. See, in the previous equation, we have a ratio between the concentration of iodine in cyclohexane and aqueous iodine, and we get the value that is 93.8, right? Now they ask, for example, if you have this ratio or this relation that iodine in hexanon, right? What will be the formula of hexanon? It would be C6H12O over aqueous iodine. Okay, now think, if I look at this solvent, isn't it a non-polar solvent? And if I look at this solvent, it's a hexanon because it have a C double bond O, so it must be a polar solvent. Is this understandable to everyone?
Yes, sir.
So I am getting 93.8, and in numerator, because it's a ketone, Rimsha, it's a ketone, and ketone have a C double bond O, and if there is a C double bond O, which means that it must have a dipole which makes it polar, but here it's a C6H12 only at this chain, so it's a non-polar. Did you understand this? Okay, so we are getting a greater value which is indicating that iodine is more soluble. Yes, Mariam, you were right. So iodine is more soluble in cyclohexane, which is non-polar, right? So as it's a polar, so it means that iodine is relatively less soluble in C6H12O, that is a hexanon, when compared with cyclohexane, right? Hence, KPC would be smaller. Is this understandable to everyone? So KPC value,
सर हेक्सानॉन में आई आई आयोडीन आयंस के कॉन्सेंट्रेशन आते होंगे ना,
iodine molecule, iodine is not an ion.
लेकिन आई नॉट अटैच हो जाएगा ना इस पे जो डाइपोल है.
Can you repeat?
The I negative, the ion.
Yes, the I negative would be the greater, but we have converted all the I negative into iodine.
Right.
Yes, but but if there is a iodide ions over there, so obviously it must be relatively more soluble in hexanon as compared to cyclohexane.
Right. Okay.
So the KPC value would be lower. Because that hexane 2 on is polar we can write it's more polar than cyclohexane, so iodine is less soluble in hexane 2 on when compared with cyclohexane. Is this understandable to everyone? Okay. The group 1 iodides all form stable ionic lattices and are soluble in water. Define enthalpy change of solution. Yes, can anyone? Nobody remember the definition?
It is the enthalpy change to dissolve 1 mole of compound to make a dilute solution.
Okay.
Ionic compound.
It's not necessary that it can be ionic. It is the enthalpy change when 1 mole of a compound, and specifically you can say, solute as well, because sometimes a substance and element can be dissolved in water as well. So 1 mole of a compound or a solute dissolve in very large amount of water to form very dilute solution. Next, use the data in table 1.1 to calculate the enthalpy change of solution of potassium iodide. Okay. So if you see over here, you see we can mark it as the lattice energy of potassium iodide, because the gaseous ions are turning into an ionic solid. The gaseous potassium ion is turning into aqueous potassium ion, makes this enthalpy change as enthalpy change of hydration of potassium ion. Gaseous iodide ion is turning into gaseous aqueous ion. This makes this enthalpy change of hydration of iodide ion. Okay. If you guys remember the expression, you can do with the expression as well. But if you make an Hess cycle, then it would be more easy to understand. See, I have a aqueous potassium ion and I have a aqueous iodide ion. Both are forming potassium iodide solid. Okay, Taha, let me check. And I can put a value of minus 629 over here. Then here beneath, if I take aqueous potassium ions and aqueous iodide ions, so if this solid turns into these, then it would be basically the enthalpy change of solution. And when these aqueous ions turn into these gaseous ions, then it is the hydration of potassium and the hydration of iodide. So if you see, you can clearly indicate that this is your direct route, and from here to here, and then here is your indirect route. So the expression would be minus 322 plus minus 293 is equals to minus 629 plus x. So x would be minus 322 minus 293 plus 629. Yes,
Sir, plus 14.
plus 14. Is this clear to everyone?
Yes, sir.
Suggests the trend in the magnitude of lattice energies of group 1 iodide, lithium iodide, sodium iodide, and potassium iodide. Explain your answer. Okay, so we have a same negative ion iodide Then we have, for example, lithium ion of this size, sodium ion of this size, and potassium ion of this size. So if you see, the charge remains same and the size gets bigger, which means there is a decrease in the charge density. And if the charge density is decreased, then the attraction between these ions also gets decreased or becomes, you can say less exothermic, because the lattice energy is always exothermic. And it is because due to the lesser attraction. So I can write that from lithium ion to sodium ion to potassium ion, the size of cation gets bigger while the charge remains same. Guys, just give me a minute, please. Okay. So while the charge remains same, and that is +1, hence there is decrease in charge density. So the attraction gets weaker and the lattice energy change gets less exothermic. Is this understandable to everyone? Okay. Now next part. The concentration of Cu2 positive ions in a solution can be determined by the reaction of Cu2 positive ion. Yes, we can write a less. Please. Yes, Taha. Okay. Yes, Ramsha, we can write that it gets less exothermic, but the more appropriate way of expressing that change is either writing gets less exothermic or writing that it gets or it becomes less negative. Okay. So in this part, the concentration of Cu2 positive ion in a solution can be determined by the reaction of Cu2 positive ion with the iodide ions. And here we have an equation. Okay. The iodine produced in reaction 1 is titrated against the solution containing thiosulfate using a suitable indicator. Okay. And here we have this reaction. If you recall this suitable indicator for the iodine and thiosulfate, we normally use starch. Remember, we always use starch for these kind of titration. A 25 centimeter cube portion of Cu2 positive solution was reacted with excess of iodine. The end point of the titration occur when 22.30 centimeter cube of 0.150 mole per dm cube thiosulfate ions is added. Okay, calculate the concentration of Cu2 positive ion. So see, we have a volume and the concentration of thiosulfate only. So first what I can do, I can find the moles of thiosulfate which is equals to 0 concentration times volume, and volume must be in decimeter cube. So 0.150 times 22.30 divided by 1000. Can anybody tell me the answer?
Sir, 3.35 exponent minus 3.
Can you repeat, Taha?
3.35 exponent minus 3.
3.35 exponent minus 3 are the moles of thiosulfate. Okay, now the thiosulfate reacts with iodine in 2:1 ratio, and that iodine is actually came from here. So first I will find the moles of iodine. That must be equals to 3.35 exponent minus 3 divided by 2. Can anybody tell me the answer? Wait, Rimsha. Yes, we are dividing because we have to find the moles of copper. Okay. Why we have to find the moles of copper? Because we have to find the concentration of copper. So first you would divide, then you will get the moles of iodine, and that iodine, if you take the ratio over here, that is again 2:1, which means that would be the same number of moles as as the moles of thiosulfate over here. So I just want to show the working to everyone, so there would be no confusion. So can anybody tell me the answer?
Sir, 1.675 minus
1.675 10 raised to the power minus 3. So these are the moles of iodine. Okay, and these moles of iodine are actually produced in the reaction 1. So according to the reaction 1, 1 mole of iodine is produced by 2 moles of copper. So to find the moles of copper, I have to multiply these moles with 2. So if you can understand initially, so you can just do this thing only, just the first step. Don't you, there is no need to show these stages as well. So I'm going to get again 3.35 exponent minus 3, and these are the moles of copper 2 positive ions, right? But I have to find the concentration of copper 2 positive ion. So the concentration of copper 2 positive ion is actually equals to 3.35 exponent minus 3 moles divided by 25 C over here. The volume of copper used is written, divided by 1000. So I have to convert it into a dm cube. So can anybody tell me the answer?
Sir, 0.134.
Okay. So it is 0.134. So it is 0.134 mole per dm cube. Is this clear to everyone? Okay. Identify the suitable indicator for the titration. I have just told you about the indicator that for thiosulfate and iodine titration, we always use the starch as the indicator. Okay, now next part, copper 1 and copper 2 both contains electrons in all 5 3d orbitals. They sketch a shape of dxy orbitals on the axis provided. So if they have given you dxy, which means that the d orbital, its orientation or its position is actually, it must be between x and y axis. Okay, it must be between x and y axis. So it could be drawn like this. It could be drawn like this. Okay, we have to show these 4 lobes between these 2 axes because they have written xy. Now question number 1D. The reaction of iodide ions with persulfate ions can be catalyzed by Fe3 positive ions. Write equations to show Fe3 positive ion catalyzes this reaction. So if you recall and if you remember the examples that we did in kinetics, we have to show those equations as well, or those equations only. So if you see over here in this equation, okay, we have to use Fe3 positive ions. So Fe3 positive ions first convert into Fe2 positive ions and then gets back into Fe3 positive ion again to show that it's a catalyst. So it means when they are converting into Fe2 positive ions, that could be a reduction and then oxidation. So it means first iron 3 positive ions are going to be reduced. So if they are going to be reduced, it means they are going to be the react with the one which is undergoing oxidation. So have a look over here. We can easily figure it out that iodine have a -1 oxidation number and here the iodine oxidation number is 0. So it means if it's changing from -1 to 0, so that is oxidation. Okay. Now, if you look over here on this sulfur, can anybody tell me the oxidation number of on these 2 sulfurs? Yes, it is -16. Net charge is -2, which means mine +14, and each sulfur have a +7. And if you work on the charge over here, the sulfur in the sulfate is always +6. And here it's -8 and the net charge is -2. So see, it is changing from +7 to +6, which means reduction. So if I'm using Fe3 positive ions, so these Fe3 positive ions are going to react with the iodide ions forming iodine and Fe2 positive. So if you see here, there are 2 iodide ions turning into iodine molecule, which means loss of 2 electrons occur, right? And here from Fe3 positive to Fe2 positive, only gain of 1 electron. So I have to multiply, I have to put the coefficient 2 before both the irons. So this would become the gain of 2 electrons. So that would be your first equation. And in the second equation, 2 moles of these Fe2 positive ions are going to react with peroxydisulfate S2O8 2 negative, forming sulfate ion and iron 3 positive ion. So if you see over here, from here to here, from peroxydisulfate to sulfate, there are 2 sulfur atoms which are turning from +7 to +6, which means gain of 2 electron. And here I have a 2 moles of iron turning 2 positive ions turning into 3 positive. So loss of 2 moles of electrons. So the electrons are balanced, which means my equations are correct. So you have to write these 2 equations. And most of the time, examiner asks specifically this example. Okay. Now, an orange precipitate of HgI2 forms when Hg positive ions, 2 positive ions, are added to Ki. The solubility of HgI2 is 100 exponent minus 7 gram per dm cube. Calculate the solubility product of HgI2, and here they have given you the MR as well. Okay. So first what I can do, if I know the MR of mercury to iodide, so I can easily find the number of moles. 1.00 exponent minus 7 divided by 454.4. Okay, it is not just the moles, it is actually can be the concentration as well. Why? Because here the unit is gram per dm cube. So if I can divide it by the MR, I'm going to get mole per dm cube. So can anybody tell me the concentration over here?
I said 2.2 into 10 to the power negative 10.
Sorry, can you repeat? 2 point?
Sir, 2.2 into 10 to the power negative 10.
Is it 2.20? Yes, Rafael.
Yes, sir, it is 2.20.
Okay. Into 10 raised to the power
Negative 10.
negative 10. So this is actually the concentration of HgI2. If I write the equation for the enthalpy change of solution or for the dissolving of this partially soluble salt, it would be like this only. So it means, if you see, there are 1 mole of mercury and there is 1 mole of mercury iodide. So the concentration of mercury ions would be exactly equal to the concentration of mercury iodide. And the concentration of iodide is actually equals to twice of 2.20 exponent minus 10 mole per dm cube. So from this equation, if I write the KSP expression, it would be concentration of mercury ions times concentration of iodide ion raised to the power 2. So it would be 2.20 exponent minus 10 times 2 into 2.20 in exponent minus 10 whole square. Can anybody solve and tell me the answer?
Sir, 1.07 10 raised to power minus 29.
दोबारा वैल्यू बताइएगा. Can you repeat your value please?
Sir, 1.07 10 raised to power minus 29.
1.07 into 10 raised to the power minus 29. Yes, can anybody cross check this value as well?
I'm getting a different value. I'm getting
What-
4.26.
सर मेरी 4.26 एक्सपोनेंट माइनस 29 आ रही है.
जी मेरी भी same है.
Okay. Check your correction calculation with the
सही है सर, मैंने 2 से मल्टीप्लाई नहीं किया था.
Okay. 4.26 yes 4.26
Into 10 to the power minus 29.
into 10 raised to the power minus 29. 4.26 into 10 raised to the power minus 29. And now units. So we have a 1 concentration and 1 concentration square. So the unit would be mole per dm cube whole cube, which actually equals to mole cube and dm minus 9. Is this understandable to everyone?
Yes, sir.
Okay. Now, question number 2. Silicon is the second most abundant element by mass in the Earth's crust. In industry, silicon is extracted from SiO2 by the reaction with carbon at over 200 degrees Celsius. And here we have the reaction. Explain why the entropy change of reaction 1 is positive. Yes. Who can answer this?
It's changing to liquid and gas from solid.
Okay,
So
good.
the randomness in the system decrease.
Increases, not decrease.
Yes, the randomness
So-
is going to
so-
increase.
Increase. Sorry, yeah, it's the number of gas molecules increase.
Yes, the number of gas molecules are increased, or the gas and a liquid is forming from the solids. A liquid, 1 minute please. And gas is formed from solid. Reaction 1 is highly endothermic. So it is the effect of an increase in temperature on the feasibility of this reaction. Explain your answer. Okay. So if you rewrite the equation over here, it the gives free energy equation. Okay, so see over here, this value is positive, entropy is positive. Okay, so if the temperature is raised, then if the temperature is raised, then this T delta S terms becomes more negative, and as a result, uh, the whole value would be negative and the reaction gets more feasible, right? So I can write that due to increase in temperature, T delta S gets bigger and it actually gets bigger than delta H, and also T delta S becomes, no, not becomes, is negative, right? So we just write this, that the whole thing minus T delta S is negative. So the change in Gibbs free energy is also negative. Hence the feasibility of reaction increases. Okay. Now, if the reaction is exothermic, okay, Rimsha. For example, if this reaction is exothermic, then it doesn't matter whether the T delta S would be greater than delta H or T delta S would be smaller than delta H. In any case, yes, then in any case, Gibbs free energy is always remains negative. Okay, Rimsha? It's for everybody else as well. But in this case, when the Gibbs free energy is actually, this is the case when we are talking about when the Gibbs free energy is negative. But when the Gibbs free energy is positive, then there could be two scenarios. If the T delta S is actually greater than delta H, then Gibbs free energy is negative, so the reaction gets feasible. But the other condition, if the T delta S is actually less than delta H, then the value for the Gibbs free energy is positive and the reaction gets actually non-feasible. The reaction becomes not feasible. Okay, Ramsha? silicon is purified by first heating it in a stream of HCl to form SiHCl3. The SiHCl3 formed is then distilled to remove the other impurities. Okay. Here we have the equation. The table 2.1 shows some standard entropy data. Use the data in 2.1 to calculate the entropy for the reaction 2. Okay, here we have the reaction 2. Whenever we have to find the entropy of a reaction, that entropy of a reaction is always equals to the entropy of the products minus sum of entropies of the reactant. Sum of the entropies of the product minus sum of the entropies of the reactants. Okay. So in the product, we have 1 mole of a hydrogen. Its value is 131 plus in product we have a 1 mole of SiHCl3 314 its value minus 3 moles of HCl. So 3 times 187 and 1 mole of silicon is 19. Yes, just put the values in the calculator and tell me the answer.
Sir, negative 135.
Negative 135. Okay, it is negative 135. Okay. Now, reaction 3 is the reverse of reaction 2 and is used to obtain pure silicon. Okay. And here we have the enthalpy change. Use this information and your answer to B1 to calculate the temperature in Kelvin at which the reaction 3 becomes feasible. Is it 135, right? Minus 135. Show your working. Okay. So if it is minus 135, so the entropy for this reaction would be positive 135 because it is just reverse of the previous reaction. Okay. Now, they are saying what we have to do, we have to calculate the temperature over here at which the reaction 3 becomes feasible. So when we talk that it becomes feasible, it is the condition when the Gibbs free energy value is equals to actually 0. So Gibbs free energy is equals to delta H minus T delta S. Delta H is equals to 0. Delta G is equals to 0. Delta H is equals to plus 219.3 minus temperature that I have to calculate and the entropy changes positive 135. But see over here the unit is joule. Gives free energy unit and enthalpy change units are kilojoules, so I have to divide it by 1000 to convert into a joule. So if I would find T, then T is actually equal to minus 219.3 divided by 135 over 1000. Yes, can anybody calculate and tell me the answer? Yes, can anybody tell me the answer?
Minus 164.
Sorry.
Minus 164.
How it could be minus?
And minus the sign होगा
सर माइनस से आ रहा है, वो माइनस बाद में कैंसिल हो जाएगा
1 minute.
क्योंकि टी का भी नेगेटिव है.
Yes, that minus would be cancelled out. Actually, 1 minute, sorry. It could be like this, that T is equals to, yeah, T is equals to 219.3 over 135 over 1000. So it is 16. Yes, what is the answer?
1624.
1624 Kelvin. So it's 1624 Kelvin. Okay. Now, next part. Silicon can also be produced by the electrolysis of SiO2 dissolved in molten calcium chloride. The relevant half equation for the cathode is shown. Okay. Calculate the time in seconds required to produce 1 gram of silicon by this electrolysis using a current of 6 ampere. Assume no other substances are produced at the electrode. Okay. So if you see over here, in this equation, there are 4 moles of electrons forming 1 mole of silicon, which means 4 times 96500 coulomb is actually used to produce 1 mole of silicon. And if you look at the AR of silicon in the periodic table, you will find it's 28. So the 28 grams are being produced. In the experiment, 1 gram is being produced from, and the time used over here is 6 amperes times T. And that T would be the time. So it is 6.00 into T into 28 is equals to 4 times 96500 into 1. So T is equals to 4 times 96500 into 1 over 6 into 28. So can anybody solve and tell me the answer in seconds? Yes, I'm sure 2276.2. Can anybody recheck 2276.2? Is it the answer?
Sir, 2297.62.
2297.
Yes, sir, 2297.62.
2297.62. Further, any other answer? Okay, just check. Is this value is correct or wrong?
The MR of silicon is 28.1.
Okay, so if its AR is 28.1, then by putting 28.1, what answer we are getting?
2289.4.
Okay, then it would be 2289.4. 2289.4 seconds. Okay, so we will continue from here in our next class, and hopefully our next class will be tomorrow. I will be share the schedule or the time in the tomorrow morning for the class. Okay. Okay. See you everyone tomorrow. Take care. Allah Hafiz.
Allah Hafiz, sir.